Okay, this video is going to help us review finding complex zeros of a polynomial. And we're going to start off by looking at the graph of y equals x to the third minus 9x squared plus 24x minus 70. So go ahead and take a minute to graph that. You can go ahead and pause the video, and then when we come back, we'll look at the graph itself, and we'll talk a little bit about that. Okay, there's a couple of things we can see from looking at this graph. I don't know what you did with your window, but I zoomed out a lot so we could see the general shape. We can see that it's a third degree polynomial, so it has this general shape to it. Right, it's an odd degree, so its end behavior looks somewhat specific. But we see here that there's only one real zero. So we want to be able to find that. So take a minute, go ahead and find that zero. Again, you could pause the video, and then we'll come back on the next slide. We'll talk about what that is. Okay, so we can see after we zoom in a little bit that this 1, 0 right here occurs at x equals 7. Now what we have to do is we have to use that real zero to break this polynomial down a little bit more, a little bit further. And we can use that zero to factor, so let's do that. What we'll do is we'll use synthetic division with that 0, x equals 7, and let's see what we get once we break this down. So here are my coefficients. Right, I automatically bring down that first number. 7 times 1 is 7, and I go about the synthetic division process. Oops, sorry about that. Should be 10. Okay, and obviously when we do this, if we are using a 0, then what should happen is we should get a remainder of 0. If we're using 7 here and that is a real 0, then we definitely should not have any remainders coming up. Okay, so now in factored form, this polynomial would look like this: x minus 7 and x squared minus 2x plus 10. So now what we know here is that if there's one real 0 but the degree is 3, there's a quantity of 2 powers that are left out. And those 2 powers would yield what we call complex zeros. Zeros that you can't see, they're imaginary, however they're hiding somewhere and they're in the form of I. So the question is, how do we find them, right? Well, they all come from this remaining expression. And if you notice, this is a quadratic, right? So that allows us then to be able to use the quadratic formula. So A here would be 1, B would be negative 2, and C would be 10. Now what we have to do is we have to use the quadratic formula to solve that particular quadratic. So let's see what we get. Remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So again, remember, a was 1, b was negative 2, c was 10. So that means really start with a positive 2 plus or minus negative 2 squared minus 4 times 1 times 10. And all that is over 2 times 1. So when we solve that inside the radical, we evaluate that, we get negative 36. Obviously we can't take the square root of negative 36, so what happens is that becomes plus or minus 6i, right? If we simplify a little bit by factoring out that 2, we can then cross out the 2, right? And so our complex zeros are 1 plus 3i and 1 minus 3i. Now remember, there's a property that exists that says the number of real zeros plus the number of complex zeros has to equal the number of the degree. So in this particular problem, the degree was 3. There was one real 0. There are 2 complex zeros, and that's how we get our 3.